Okay. So we started multi-objective optimization, and we introduced the concept of dominance, which is a very important concept for multi-objective optimization. We need it, or the selection process in single objective, we select based on the objective value. But here in multi-objective, we are not selecting based on the objective values, but based on dominance. And we defined what is non-dominated solutions and the dominated solutions. Okay, so we went through all this part. This is the general formulation of the multi-objective optimization. You have several objectives that needs to be optimized simultaneously. So we introduced, or we discussed, the concept of dominance, conditions for the solution to be non-dominated or non-covered solutions. So and we introduce also this example, so that you can see here 1, 2, 3, 4, 5, 6, 7 are the non-dominated solutions, non-covered, and these are the solutions that we are targeting to get. As you know, the output of the multi-objective optimization technique is not a single solution, but a set of solutions. And these solutions is called the Pareto optimal solutions if you reach to the final stage. At any generation, we call these solutions as non-dominated solution. And one of the objectives for multi-objective is to find or to push the search towards the optimal solutions here. And also another objective for multi-objective optimization is to keep these solutions are well distributed. We need to have a diversity of the Pareto optimal solutions. So this is the covering concept. So we need to guide the search toward the Pareto optimal region, and also we need to maintain the population diversity. And as we have it here, this is the Pareto optimal front, or we call it Pareto optimal set, or Pareto optimal solutions. So as you can see here, for this example, we have set A and set B. On set A, which is the red color here, is better than set B in terms of quality of the solutions. These solutions are non-dominated. These are dominated solutions, so set A is better. And here also set A, which is the red color here, is better than set C in terms of the diversity. So you can see that set A is well distributed over the front. So this is for minimization problem. So we need to, minimization problem, we need to push in this direction. For maximization problem, the things are flipped. For maximization problem, as you can see here, we have 7 solutions, 1, 2, 3, 4, 5, 6, 7. So you can see in maximization problem, we need to push in this direction. So these are the blue solutions here are the Pareto optimal front. These are non-dominated solution. So this solution covers how many solutions? Does this solution cover? Can anybody tell us how many solutions are covered by this one? This is the maximization problem. And if the objectives y1 and y2, the higher the objective, the better the solution. So what do you think? Any answer? How many solutions covered by this one? Muhammad Ibrahim, Muhammad Abdul Rahman?
4 solutions.
4 solutions. All solutions in this region are covered by this one. And this solution covers one solution. This solution covers 2 solutions, this one and this one. For this solution, for example, whatever here in this gray area is covered solution or dominated solution. This solution dominates this one, or this one is non-dominated with respect to this one, but definitely this one is also covered by this one. So whatever here is better than this one, whatever in yellow region here. This one and this one, for these 2 solutions, which one dominates the other? Can anybody tell us? For this solution and this solution, which one dominates the other? Muhammad Tar?
Yes, they are non-dominated.
Yes, none dominates the other. None dominates the other. This solution and this solution. So, okay, so these are, with respect to each other, they are non-dominated solutions. Okay? But in general, for the whole population, for the whole 7 solutions, 1, 2, 3, these blue solutions are the Pareto front, or the non-dominated solution. So this is the Pareto optimal, non-dominated, and all these yellow colors are dominated solutions. So this is for maximization problem. The concept can be, twisted for maximization problem, no problem. So the objective here is to push the solutions in this direction, and also the second, second target also is applied here. We need also the solutions to be well distributed over the Pareto front. Okay, so we would like here to, in this part, to go over the classical or traditional multi-objective optimization methods in order to see the limitations of the traditional multi-objective optimization methods, and also to identify the advantages of multi-objective evolutionary optimization techniques. So let us see the classical methods. Classical method, as we mentioned earlier, we have weighted sum and epsilon constraint and the goal programming that we will see. Knowing that a genetic algorithm or any technique, single objective, needs a scalar fitness information to work, it is almost natural to propose a combination of all objectives into a single one. And the idea behind the traditional multi-objective is to convert the problem to single objective. by aggregating all the solutions or all the objectives together. Several techniques have been developed to handle multi-objective optimization. These approaches are normally known as aggregating approaches. The most probable aggregating approaches are discussed in the following section. The first one is the weighted sum method. The weighted sum method is simply you combine all the objectives together in one by sum of the weighting factors. This method consists of adding all objectives using different weighting coefficients for each one of them to form scalar optimization problems. So this is now the objective, and we convert from minimize F1, F2, and F3, and F4 to minimize single objective, which is the summation of all objectives with the weighted factor here. And this weighting factor reflects the importance of the objective with respect to the decision maker. So this is the transformation of the from multi-objective to single objective. The weighting is greater than or equal 0 and the summation equal to 1. It is usually assumed that the summation of all weights equal to 1. So you have a number of objectives equal to 2 or 3. So you have W1, W2, W3. Summation of all these objective weights equal to 1. So this is the weighted sum. However, all functions should be expressed in units of the same numerical values by using constant multipliers. And you can have, definitely if you combine several objectives together, you have to make sure this is minimize. You have W1 F1 plus W2 F2 plus W3 F3 and so on. So you have to make sure the order of these terms are the same as a magnitude. So this one is approximately 100, for example. This objective ranges between hundreds plus and minus. And this is, for example, 10. And this is 100. This is objective. This is an order of tens. This is an order of 0.1, for example. This objective is 0.1. You have an index of voltage stability or whatever. So the index is between 0 and 1. So this objective the value is between 0 and 1. If you combine them as such, definitely this will negatively affect the solution. You have to make sure all these terms are in the same order. So we might have a scaling factor here to multiply this by 10. So 10 times 10 is almost 100. And we have to multiply this by 1000 as a scaling factor in order to have it almost 100. Unless otherwise, you may improve one objective at the expense of the others. And for example, if this solution, if this objective is 100 and this is 10, and you need to minimize all the objectives. So you may, in one of the solutions, can give you this F1 equal to 90. And this gives you F2 equal to, for example, 15. So 90 is better than 100, you are minimizing. 15 is worse than 10. But generally, you have a summation here. 90 plus 15 is 105. And this one is 110. And you assume you are minimizing, but you are minimizing for one objective at the expense of the other, which is not, of course, needed here. We need to minimize all the objectives. So we need to minimize this objective and this objective as well. So this is why we need to have all the terms in the same order. So otherwise, you need to here multiply by the scaling factor, and this is a weighting factor to reflect the importance of the objective, and this is the scaling factor, which is maybe 10 or 1000, as we have in the last example. So this is the now the objective. If you want to skip for this scaling factor, you can normalize the objectives. Yani alternatively, we can say here alternatively normalize all the objectives. And make all the objectives between 0 and 1, in the range between 0 and 1. How can you do this? You can divide this if normalized, fi equal to the actual value of the objective minus fi minimum over fi maximum minus fi minimum. So you divide over the maximum and the minimum. So in this case, you have this normalized value between 0 and 1. If I equal to fi minimum, so it becomes 0. If this is equal to maximum, this becomes 1. In between, you can have a value between 0 and 1. So instead of this scaling factor, you can have the normalized objective function as such. So it becomes now wi times fi minus fi minimum over f max minus f minimum. So this is the summation here. So this can be done. The main strength of this method is its computational efficiency. You have single objective. You are going smoothly with any technique, traditional techniques or single objective techniques, genetic algorithm, differential evolution, or whatever. So you can proceed smoothly. However,
Excuse me, Doctor.
Yes, please, Mohammed. Go ahead.
Yes. I have a question. How to set this constancy? Do we solve the individual objective individually in order to know this?
This one, C.
Yes.
To avoid having this C, you can normalize the objectives. If you normalize the objectives, so all the objectives now becomes between 0 and 1. So you don't need this C.
Yeah,
Did
I
you agree
understand.
did you agree with this?
Assume I want to put the C.
If you want to put the C, usually this Wi is the weighting factor, right?
Yes.
So you can, at the beginning, you can have only one objective. And you can have run number 1 of the technique. You consider only F1. You optimize only F1. Okay?
Yes.
You optimize only F1. Yeah, assuming that you have here this weighting factor is 1, F1 plus 0, F2 plus 0, F3. So you are concentrating only on the first objective function, cost, مثلا, for example. Okay? So you minimize the cost. So you know the order of the cost. You know the minimum value of the cost. Okay. So this is the cost value. And also, run number 2, you consider only F2. So you get the minimum value of F2. And the run number 3, again, you can have similar. You consider only one objective, which is F3. So you can know the order of these objectives. Okay?
Yes.
Is it clear?
Yes. The second question here is, after I combine the objective, then I need to divide by W and C in order to get the correct value of the objective, correct?
No, you don't need, no. No.
After I solve the problem,
Yes.
now the f of I, let's assume that the value will be actually multiplied by W and multiplied by C.
Okay.
Then
But
I need,
you don't need this value now. If you solve the problem,
okay,
you have the optimal solution X, then you can substitute for F1 and you can get it. You can substitute for
okay,
F2
okay,
and you can get it, and so on. So this is the combined, it is meaningless. Okay?
okay, okay.
And
It's like a dummy or
yeah,
augmented.
exactly. This is يعني some kind of dummy fitness or dummy objective function. But this one you can have the value, exact value of the objectives after getting the optimal solution. Okay?
Yeah, one last question here. Is there a range for C, for example, as per your example, you said is 10. Is there a like 20% range of C, or it has to be exact after I solve?
When you solve F1 and you get the value of F2 and you know the order of the F3, so you can, but this also, it is not, يعني these values are subjective. It is not
Yes.
يعني exactly set. يعني and I just put 10 here or 1000, but maybe this value is يعني we are not يعني trying to get it exactly. يعني this is subjective. يعني this could
Okay.
be 90, this could be 110, this could be يعني يعني around it. But you
Okay.
have to do it. Otherwise, as I mentioned here, this is the drawback of not
Oh,
scaling
yes.
the.
Thank you, Professor.
So this is the way it is done. The main strength of this method is to computational. يعني you can go smoothly with the any objective, any evolutionary techniques that we have before. However, of course, there are some difficulties and drawbacks for this method. Its main weakness is the difficulty to determine the appropriate weights. The weights also are subjective. And the weights والscaling factor are subjective. يعني for example, if you have W1 F1 plus W2 F2 plus W3 F3, if you have W1 equal to 0.3 and the W2 equal to 0.4 and the W3 equal to 0.3, summation equal to 1. So in this case, what does 0.3 means? Yani? What does 0.4 means? Yes, it reflects the importance of this. But if you, for example, set another weights here, W1, if you set it equal to 0.2, W2 equal to 0.5, and W3 equal to 0.3, you will end up with different solution. Yani here, the optimal solutions are different. X star and X star here, they are different solutions. Once you change the weights, you will end up with another solution. You change the weights, you will end up with another solution, and so on. So if you want to create the Pareto front using this method, in this case, you will start assuming that we have only, just for clarification, we have only J1 and J2, or F1 and F2. This is the first objective, and this is the second objective. So assume that, and we have, if you have W1, you can say here, we can create a table for W1 and W2. We can start with W1 equal to 1, then W2 equal to 0. So as if we are minimizing only the first objective function. We are minimizing this one. So definitely we will get the very small value of F1 here. We need, after getting the solution, we can substitute in F2 and you can get its value. And if these are conflicting objectives, but definitely with a smaller value of F1, you have a greater value of F2. And then you move forward. Let us take this 0.9 and this is 0.1. So you will end up with another solution, which could be here. And you can get to 0.8 and 0.2, then you will get another solution here. And you can go forward until you have here 0 and 1. So as if you are minimizing the second objective function, so you can go here. So this is the best solution for F2 and this is the best solution for F1. So you can, by changing these weights, you can get the Pareto front here, okay? So this is the way you can change the weight. By changing the weights, you get other solution. But in this case, you need to, if you want to create the Pareto front, you have to run the technique several runs in order to get several solutions here. In addition, it doesn't generate proper Pareto optimal solutions in the presence of non-convex search spaces. If you look at W1F1 plus W2F2, this represents what? As an equation, represent what? Represent straight line equation. Am I right? Hakami, do you have a question or answer?
I have an answer. It should represent the fitness for me. It is my objective at the end.
Yes, this is the objective. Now, but W1F1 plus W2F2, this represents what? As an equation of a straight line. Am I right? For example, if you have 3x plus 2y equal to constant here. So at the end, this will be equal to constant. So you have here 3x plus 2y equal to a constant here. So this represents what? Straight line equation, right?
Yes.
And based on these coefficients are playing with the slope of the line. So if you change this to B1 and this is 0.1, you have a straight line as such, you have another straight line as such, you have another straight line as such, and so on. So if you have only x, then x is constant, so this is a straight line. If you have only y, if you have only y, if this is 0, so y equal to constant, but this is the straight line. So changing these coefficients, changing the slope of the line. And this is the problem with this line, with this technique. And if you have non-convex search space, if you still remember at the beginning of the optimization, we say no, for example, this search space, again, let us make it more pronounced. For this one, for this search space, this is convex or non-convex? Convex or non-convex, this search space?
It's non-convex.
Non-convex. Why? And if we have two solutions, one here and one here, if this is convex, if all interpolation, all points in this line will completely lies also in the search space. And طبعا this is Let us put it as such. If this is the search space, this is non-convex. This is non-convex search space. Why? The definition of the convex search space, and if you have any two solutions, the all solutions should be completely lie in the search space. But if we have a solution here and a solution here, and if we interpolate between these two solutions, you can see in a part of this line is outside the search space. But this search space is non-convex. And this is a problem with this line. If you have such a search space, this is non-convex. And if with this objective you are trying to changing the slope of the line, so if you change the slope of the line, are you able to identify this part of the Pareto front? Is there a line that will be a tangent for this search space at a certain point?
No.
This is the line, straight line, you have a certain W1 and W2. If you change the slope of this line, okay, we need, for example, another line like this one. So this is a tangent point. Okay, another line with different W1 and W2. So we will identify this point. And play with the weight W1 and W2. Of course, you will not find, we need, of course, the equation or this equation to be a tangent of it's not intersecting. And we cannot say, no, this will give us this point. No, this is not the case. The extreme point or the optimal point will be the tangent of the line with the search space. In this case, we will not identify this part using this method. So this part will be hidden, will not be identified. So what we can get, if you change W1 and W2 100 points, for this non-convex search space, you will end up with few solutions clustered here and a few solutions clustered here. And that's all. So you will not find, of course, this well distributed as such, but you can have some solutions here and some solutions here, and these will not appear with this weighted sum method. This is the major problem for the weighted sum method. The Pareto front, some of the parts of the Pareto front will not be detected if the search space is non-convex. Okay, so yes, if you change the weights here and there, so you will end up with this part that you can identify and this part that you can get out of the Pareto front. Nasser?
Yes, Doctor, I have a question, but in the previous slide for normalization. Yes, we have the equation of Fi actual and Fi minimum and Fi maximum. The Fi is our objective, our fitness. So actually we are looking for the equation for our Fi minimum. So if I don't have that minimum, so how I am putting this on normalization? And the second question, the same time, sometime if I'm looking for minimum or maximum objective, the other side maybe will be infinity. For example, the maximum will be infinity if I'm looking to the minimum. So.
Okay, well, usually here, if minimum, if maximum, if minimum, and so on, you identify within the generation that you have. And at the beginning, you have initial population, right?
Yes.
You have G0, initial generation. You have randomized the solutions, and each solution to calculate J1, J2, J1, J2 for all solutions here and there and so on. So for J1, you can know J minimum and J maximum. For J2, you can also identify where is J minimum and J maximum, right?
Yes.
Is it clear? So you know J minimum, F minimum and F maximum. You know the minimum value and the maximum value here for each objective. And when you want now to weight sum of J1 and J2, you have W1 J1 plus W2 J2. You can, instead of J1, you can have it normalized now. This value, you can normalize it having this minimum and the maximum. Okay? Is it
Okay,
clear?
now clear. Yes,
And
clear.
also you will do this again for for the first generation, second generation, third generation. At each generation, you can have J minimum and J maximum for each objective, and then you can normalize.
Okay, thank you.
Okay. So,
Doctor,
yes,
just a quick question about the same slides before a moment. When we consider running different, when we consider having different runs, for example, not this one, the previous one.
okay.
Yeah. So we consider only F1, and then we consider only F2 and F3. Does this mean that we ignore the rest by enforcing them to be 0?
Not enforcing the values. Not enforcing the values. You set a W equal to 0. Okay? But definitely,
Like
after solving this, you have a solution. You have X1. You take this solution and find the F2 and find the F3 and find the F4, whatever the objectives here. So you take this, but this solution gives you the minimum value of F1. But if you have conflicting objectives, this one will be the worst for F2. You can calculate F2, you can calculate F3 without optimization. At the end of the optimization, you have the optimal solution, and you take this optimal solution and find the values, corresponding values of F2 and F3. And for this one also, you have the optimal solution, and then you can calculate F1, F3, F4. And for this one, you have the optimal solution with respect to this, and you go and calculate F1, F2, and F4, and so on. So when you neglect in the optimization, you consider only one objective. This is my target. And after getting the optimal solution, you can calculate the corresponding objectives.
Okay.
Is it clear?
Yeah, clear. Yes. Okay.
So at the end, as I mentioned, you can have some clusters here of the as we mentioned earlier, on multi-objective, we need to have a well-distributed over the Pareto front. So you have here some of the solutions are hidden completely if you have the weighted sum method. Of course, if you have multi-objective evolutionary algorithms, in this case, you will see well-distributed, and all the parts or all the regions will be identified by multi-objective evolutionary algorithm. As we will see later, what are these techniques and how it works. Another traditional multi-objective optimization is the goal programming. For the decision maker has to assign targets or goals to be achieved for each objective. And for example, if you have cost, مثلا for example, cost and reliability. You can set your target in terms of the cost. You know the cost is between مثلا 100 and 300 مثلا. This is the cost. Let me put the target as 50. This is our target. The target here or the goal here should be outside the feasible region. And this is the problem with this method, by the way. And you have to have a prior knowledge about your search space in order to set the target. We need this target to be unfeasible, to be outside the search space, and we will see why now. And for reliability also, you need to assign a target. You know, the reliability, for example, is an index could be between 0.5 to 0.9 مثلا. So let me put it 0.2, which is far from this. We will see these values are incorporated into the problem as traditional constraints, and the objective function will then try to minimize the absolute deviations, absolute difference between the solution here and the target. We need to minimize the distance between the solution here and the target, the solution here and the target. So we need to push the solutions towards the target. So at the end, if this is the range, the minimum distance will be achieved if you hit the minimum value here. So this is the nearest to 50. So this technique will give you the smallest value here, or the nearest to the target. So the objective function will then to minimize the absolute deviations from the targets to the objectives. And the simplest form of the solutions can be formulated as such. So you have here the several objectives, and each objective has a certain target. So you can minimize the distance between the objective or the solution and its target. So you sum them all the objectives here. Similar to the weighted sum, but here you are minimizing the distance between the objective and the target. So this is the objective function, where T denotes to the target or the goal set by the decision maker for the objective Fi, and omega is the feasible region. So here is the situation. This is the feasible region, and you set the target outside the feasible region, and you need to minimize the distance between any solution here and the target. Any solution here and the target. So definitely you will end up with these solutions. So these are the nearest to the target. So in this case, you end up with the Pareto optimum front. This is the Pareto front here. And of course, you are changing the weights here. You come up here by the weights, and you run it several times, and you end up with these solutions one by one. Okay? Is it clear? طبعا the limitation of this method is you have to have a knowledge about the search space. لأنه if it happens and this target is here, if this is your target, in this case you end up with very bad solutions. This is not, if you minimize the distance, you will have such solutions here, and these solutions are definitely not the Pareto front. So you are far from the Pareto front. So you have to have the knowledge about the search space in order to set the target here outside the feasible region. This technique will yield a dominated solution if the goal point is choosing the feasible domain. And its main strength, its computational efficiency in case of desired goals are known and feasible. However, of course, you need to have some weighting factors if you want to find out the several solutions, and you have to, in most cases, difficult unless you have a prior knowledge about the search space. Also, the feasible region is difficult to approach. This method could become very inefficient also. So these are some of the limitations. The third one and last one that we'll discuss here in terms of traditional multi-objective optimization, the epsilon constraint method. The epsilon constraint method is simply considers one objective at a time, and when you consider one objective, you add other objectives as constraints. So as we mentioned earlier, if you optimize, مثلا, for example, you have F1, you have F2, and you have F3. If you optimize F1 only, assume that you consider F1 only. So you have a solution, and you know what is the minimum value of F1. This is the minimum value. When I want to optimize or to get the solution for F2, I add F1 as a constraint here, but with some relaxation. يعني the F minimum here is 10. مثلا, for example, the value of the F minimum here is 10, and this is the optimal value. Let me relax it to 12, مثلا, to 15. So I can add here a constraint if one is below or equal to 15. So I do some epsilon, some deviation, which is 5 here in this example, some deviation of the minimum value. I do some relaxation and add it as a constraint here. When I come here, I add F1 as a constraint and F2 also as a constraint. When I optimize F3, I know the minimum value of F2 here. I get it, and then I will relax it by epsilon, and I will add it here as a constraint when I optimize for F3. So this method is taking one objective at a time, and the other objectives will be added as constraints with some relaxation, which is epsilon here. So this method is based on minimization of one, the most preferred or primary objective, and considering the others objectives as constraints bound by some allowable limits, which is epsilon here. So this epsilon are altered to generate the entire Pareto optimal set. You can, of course, say it if it is 12, if it is 11, if it is 14, if it's 15, and so on, and you run it again and again until you, and each time you get a solution. So when the bounds epsilon I are too low, there is no solution, and at least one of those bounds must be relaxed. Of course, if there is no feasible solution, you have to relax epsilon more, and you have to relax these constraints. And the most obvious weakness of this is that the time consuming, particularly if there are too many objectives. لأن الإبسلون, when you have an epsilon, you set it 5, but we don't know whether this F1, if it is less than or equal to 15, will give us a feasible solution or not. We may not. We may end up with no feasible solution, so we have to run it again with some relaxation and so on. So it may take some time to generate the set of solutions that you need. Furthermore, this method tends to find weakly non-dominated solution, and it eliminates some of the solution, as you will see here. The relative simplicity of the technique is main strength of this popular multi-objective optimization. So if you have such a case, you have cost and the time. You need to minimize all cost and time. This is the Pareto front. Okay, so this is what we need to find out. If you set here the time, if you set here the cost as a constraint, so this is our constraint, this is the cost. The cost should be, for example, greater than or less than, for example, 12 or 11. So in this case, you will find this solution. And if you go to another objective and do the opposite, if you need to minimize the time, if you need to minimize the cost and the time is constraints, so you will get this one. The time is constrained, so time should be, for example, 1.5. So we will end up with this solution, and so on. Of course, you have it here, so you can get this one, you can get this one, and so on. If you relax it more, you can move left and right. So these are some of the traditional techniques, and in conclusion, as you can see, for these techniques, you need prior knowledge about the feasible solution, which is not the case for multi-objective evolutionary, and also the non-convex search space, as you will not be able to find out the part of the Pareto front. And also one of the drawbacks is that you have to run the technique several times, as many times as the number of Pareto solutions that you need to find out. If you need 50 solutions, you have to run the algorithm 50 times. At each time you play with the weights and so on, or this epsilon, so you can get other solutions and so on. But for multi-objective evolutionary algorithms, since these solutions are population-based, so you can end up with the Pareto solutions in one run. In single run, you can have the complete Pareto front. And of course, this non-convexity is not an issue in this multi-objective optimization. طيب, here we want to, usually in multi-objective techniques that we will discuss later on, we will need to do some clustering if the Pareto set exceeds a certain limit. Then, as we mentioned, at the end, we need a manageable set to be submitted to manageable set for the decision maker. So we need to limit. Then at each time you have the, especially if the problem is real valued problem. If the real value problem, like what we have here, K, T1, T2, these are real valued parameters. This is between 1 and 100. So you can have infinite number of solutions as a Pareto solutions. All these points represent a Pareto front. So at each time you have some dominated, non-dominated solution, non-dominated solution. So at the end you can have very huge Pareto set here. So in this case, we need to limit the size of the Pareto optimal set by do some clustering. We need to do some clustering here. We need to eliminate some points here, and we need to have a representative and manageable size of the Pareto set. So usually in multi-objective optimization, we need clustering. And the second point also that is usually in multi-objective optimization, you get the Pareto front. So can you introduce to the decision maker the best compromise solution? This is also important. How to find best compromise solution? What are the criteria for best compromise solution? So you can say, no, this is the best solution regarding all the objectives. So we can see also how to, from the Pareto set, how can we extract the best compromise solution? So these 2 points are common in multi-objective optimization. So this is why we are introducing them here. And for any technique later, when we say clustering, you know how to do clustering. Generally, the Pareto optimal set can be extremely large, therefore reducing the set without destroying the characteristic, by the way. Sometimes of course, definitely you have some idea about clustering. So if you have, for example, here, these solutions. So how to do clustering for these solutions? How to do clustering here? What do you think?
Maybe the nearest group to
Assume that we need here, we have here 1, 2, 3, 4, 5, 6, 7, 8, 9 solutions. Assume that we need here like 3 clusters. And this is just for illustrative example. So you measure what? The one who answered here?
Those nearby points can be grouped together.
Nearest point.
Yeah, the 3 are together and the next 3 are together.
You can measure the distance here. The distance here. Distance between. You can create a distance matrix. This is 1, 2, 3, 4, 5, up to n solutions. 1, 2, 3, 4, 5. طبعا this is symmetrical solutions, definitely the distances. Here are zeros. Distance between the solution and itself. Now between 1 and 2, هي نفسها between 2 and 1. So between 1 and 2, you can get the distance. Between 1 and 3, you can get the distance. 1 and 3, 1 and 4, 1 and 5, 1 and 6, 1 and 7, and so on. You can, لأنك أنت at the end, you have solutions and you don't have, here طبعا it's clear لأنه we plotted. إنما if you have some solutions, x1, x2, x3, x4, you don't know which one is the closest to other. But here you can say, this is 1 and 2 is, but anyway, you have the solutions tabulated here. And with these solutions, you can get the distance between x1 and x2. طبعا the distance is, square root of parameter difference between x1 and x1 x11 and x12 minus distance x1 x21 and solution 1 minus the dimension 2 of the solution 2. So if the solution here is don't mix between this x1 and this x1. x1 here is the parameter. x1 here is the solution. So this x1 is x1, x2. So if you want to measure between these solutions, you take the difference between x1 square and difference between x2 square under square root. So this gives you the distance. So you can have the distance 1, 2, 1, 3, 1, 4, 1, 5, and so on. And you can have the distance also for this between 3 and others, 4 and others, and so on. So let us take this row and see what is the minimum distance to solution number 1. So you can identify solution number 2 or solution number 3 and so on. And you can see also for solution number 2, solution number 3, and so on. So you can identify which one is the closest to others. You can see here the distance minimum, D minimum of this. And for the second row, you can get the D minimum also. The minimum distance in the second row. Excluding this 0. The D minimum of the 3, D minimum of 4. And look at this D minimum and see which is the minimum of the minimum. You can see which is the minimum of those minimums. So if it is between 3 and 4, this is the minimum distance between 3. Let us combine 3 and 4. How to combine 3 and 4? We consider them as one cluster. We consider 3 and 4 as one cluster now. And then we will, calculate the distances again and again between this cluster and the other solutions, and we get the minimum and between 1 and 2. So this becomes another cluster, and we do again distances between these two clusters and the others individuals, and we can add here number 5. So 1, 2, 5 becomes the minimum, and we reduce the population or the number of solutions one by one. So at the end, we will end up with the three clusters here. The major question here is, if we have this as a cluster, what is the representative of this cluster? Now we need, at the end, we need to take, or we consider one solution here for this cluster as a representative. We have here like 9 solutions. We need 3 clusters. We need to end up with the 3 solutions only. What are the solutions that will be selected as a representative of the 3 clusters? Cluster here and the cluster here.
The minimum cluster.
The
minimum cluster.
What do you mean by minimum? Khaled?
Suppose we discuss that these 3 before one cluster. The one that is minimum amongst them will be the representative of the cluster.
These are non-dominated solutions يا خالد. المينيمم there is no one better than the other.
Yeah, okay.
And we are here, we are clustering the Pareto optimal set. And at the end, the Pareto optimal set could be infinite number of solutions if you are handling a real value problem. So all the solutions are non-dominated, so we cannot say you take the minimum. Now we need to reduce from 9 solutions to 3 solutions. The question now is that we do clustering and we combine, these are the minimum distances and this also and this also. And the question now is, what are those 3 solutions that represent this Pareto front?
Median value.
Nasser Hakami, Khaled Sulaiman, do you have an answer? Or, okay, Nasser Hakami.
The average. The average value. Yes, for each cluster.
And if you have, for example, here a cluster is 2 solutions.
If one is 12, another is 10, then I will take 11.
You will take 11.
Yes.
You have here, this is the point, or this is the representative 1.
Yes.
What do you think, ya Shabab? Can we go with the motion of Nasser? We take the average?
But it is possible to be unfeasible solution.
Yes, you are right. The average here doesn't represent a solution. And we don't know whether this average is a feasible solution or not. Did you get the point, ya Nasser?
I think it should be a solution because we are in, I'm assuming that we are in conference search base.
We are in the in objective. This is the objective space. This is J2 and this is J1. Okay, and these are the solutions.
Yeah, you are right.
If you take the average, you don't know whether you
Get,
have a feasible solution corresponding to J equal to 11 or not. This is the 10 and the 12, okay? So we cannot take the average.
we may get the parameter is out of the limit.
Yeah, exactly. So we need to select a solution that is representative to the cluster. For example, here, definitely this is straightforward. If you have 3, so the middle one will be the nearest to the average. The middle one will be nearest to the average. Is it clear? And maybe you have one solution here, one solution here, and one solution here. These are the cluster. This is one cluster. So what is the representative solution? Again, you can get the average, and you take the nearest to the average. The average could be here. So this one, this is the nearest to the average. So this solution will be selected as a representative to this cluster. Is it clear?
But we just said the average could be unfeasible solution.
We are not taking the average. We are taking the solution which is nearest to the average.
Okay.
We stick with this solution. We will select this solution. We are not inventing one solution from nowhere, but we are taking this solution as a representative of the cluster. And this solution is the nearest to the average.
Yeah, okay.
All right. Now, if you have such a case, 2 solutions here, the cluster has only 2 solutions. Which solution would be taken as a representative?
Anyone.
Any one of them. Any one of them can be taken as a representative for that cluster. Okay? Is it clear? So
could you please repeat the last sentence?
we are comparing here. If you have here like 3 solutions in one cluster, we need to identify a representative for this cluster. But this representative should be a solution. So we get the average of the 3. This solution has x1, x2, x3. So you add x11, x12, x13 plus over 3. So this is the average x21, x22, x23 over 3. So this is the and so on. Okay. And you can see which solution is the nearest to the average. Based on this illustrative example, you can say, this solution is the nearest to the average. If the average is here, for example, and in this case, we select this solution right away. So this is a representative for the cluster. Okay. So in Pareto optimal set, we will discard these 2 solutions and we keep this solution as a representative here. For this cluster, we will take also the nearest to the average, which is this one. And we take this one. And we take this one. If we have two solutions here, the average is the midway. Definitely, the average will be the midway. So we can take any one of them as the representative of the cluster. Okay? So you discard one and you take one as a representative of this cluster. Did you get the point, Khalid? Khalid was asking, right?
Yes, Doctor, I got it. Thank you very much.
Okay, so this clustering is usually the case in multi-objective, especially if you have real valued solution. The parameters are real valued parameter. An average linkage, this is one method of the clustering. An average linkage based hierarchical clustering algorithm is employed to reduce the Pareto set to manageable size. As we mentioned here, we calculate the distances and we get the minimum, and we get the minimum, and we take the minimum of the minimum. So the minimum of the minimum, and we consider them as a cluster. So this becomes one cluster. And we repeat the process again as if this is one element now. And we calculate the distance of all the solutions with this cluster. And again, we have the minimum of the minimum. But now the number of solutions will be reduced by 1. Am I right? And the number of clusters now, if you combine 3 and 4, and you consider them as one cluster, so how many clusters do we have? And for example, we have here 9 solutions. Okay? At the beginning, you consider we have 9 clusters. Each solution represents a cluster. And when you get the minimum of the minimum here, and you find out 3 and 4 have a minimum distance, so you combine 3 and 4 as a cluster. So we have now 8 clusters. So we have 8 distances here. Okay, and then again you combine, calculate the minimum, and then you get the minimum of the minimum, and you combine 1 and 2, for example. So you have now number of clusters is lowered by 1, and you repeat this again and again until you have 3 clusters only. Once you have 3 clusters, then you can select a solution which is the nearest to the average of each cluster. So you have here the output of the clustering technique. It works iteratively by joining the adjacent clusters until the required number of grooves is obtained. Abdullah Yusuf?
Doctor, I have a question. How to calculate the distance between a number and a cluster?
Okay, so we will discuss it in next slide. Of course, if you have here 3 and 4, and you have, for example, 1, you can get the distance 3, 1, and 4, 1, and you can get the average here between 3, 1 and 4, 1. So you can get the average distance between this cluster and 1. This is the distance between 1 and the cluster. Okay. We will see the formula right now. It can be described as such: the clustering technique. Given a set of B, which is its size exceeds the maximum allowable size. The maximum allowable size is N, and it is required to form a subset, P star, with a size N. As we have 9 solutions, and we need to reduce to 3 solutions only. The maximum size is 3 solutions in that example. So we need to eliminate 6 solutions, and we end up with 3 representative solutions. The algorithm is illustrated in the following steps. initialized cluster set, each individual constitutes a distinct cluster. If number of clusters is less than or equal n, then go to step 5. خلاص يعني you finish. Else continue, go to step 3, combine. Calculate the distance of all possible pairs of clusters. Okay, at the beginning we assume in each solution has a single cluster. The distance d of two clusters, C1 and C2, distance between any two clusters, is given as the average distance between the pairs of individuals across the two clusters. And for example, if you have here 3 and 4, as you mentioned, Abdullah, and you have another cluster here, 1 and 2, you can get the average distance. You can get 3, 1, 3, 2, 4, 1, 4, 2, and you get the average distance. You have 4 distances here, and you can get the average. In this form, you can apply this. This is D equal to 1 number of solutions in cluster 1, number of solutions in cluster 2. So you have N1, N2. So it is 2, 2. So this one will be 4. And you can get the distance between I1 and I2, where I1 belongs to C1 and I2 belongs to C2. Then you have the 4 distances, D31, D32, D41, D42. Okay, Abdullah? And you divide this by a number of solutions in cluster 1, a number of solutions in cluster 2. So if this is the case, it would be 4 here. So this is the distance between the clusters. Do you still have a question, Abdullah? Okay.
No, I forgot.
Okay. So N1 and N2 are the number of individuals in the cluster C1 and C2. And the function D reflects the distance of the objective space between individuals 1 and 2. So this is the distance in objective space. Yani the solution 1 has objectives J1 and J2. And solution 2 has an objective J1 and J2. So can you get the distance J1 and J2 for the solution 1, and for the solution 2 you have also J1 and J2, and let us say this is 2, 2, and this is 1, 1. This is the solution 1, and this is the solution 2. Can you get the distance between these two solutions? Of course, J1 minus J1 square, J2 minus J2 square under square root. So you can get the distance between these two solutions. Step 4. And of course, if you have other objectives, you can continue. So determine the two clusters with minimal distance DC and combine these clusters into a larger one. So as I mentioned here, of course in MATLAB you can do it in just in one. And in MATLAB, what you want to do is to search for the minimum distance in this matrix, or minimum value. Except the, of course, the diagonal. So the minimum value, it will give you the minimum distance in the matrix, and not needed to find the minimum to get the minimum of the minimum. But you can, of course, get the minimum of this matrix right away. And you combine with, for example, if this is the minimum distance here, this is between solution 3 and solution 5. So you combine 3 and 5, or 3 and 4 here. And then you repeat this again and again until you end up with the number, the maximum number that you need here. Each time you reduce by one cluster. And as mentioned here in step 4, determine the two clusters with minimum distance. So you combine them together. So we have number of clusters now reduced by 1. And then go to step 2. Repeat until you end up with the number of clusters equal to a number of, or the maximum size that you need. If you reach to the maximum size that you need and you eliminate or you cluster all the solutions, then you can find the centroid, the average value of each cluster, and select the nearest individual in this cluster to the centroid as a representative individual and remove all other individuals from the cluster. And of course, as you mentioned, if this is the cluster and you have a solution here, solution here, solution here, this could be one cluster only. And this could be one cluster. So if you have, for example, 100 solutions and you need to reduce it to 20 only, this is the maximum size. And you have Pareto set equal to 100 solutions. So in this case, definitely each cluster will have 5, 10 solutions. Maybe one solution will be represent one cluster only if it is far from the others, and so on. So if this is the cluster, you can get the centroid maybe here, and you can, of course, select the nearest solution to the centroid as the representative. So we will take this one and we eliminate all the others here. Nasser Hakami, do you have a question, Nasser? Oh.
Yes, Doctor. What is the minimum?
The time is over ب 10 دقايق دلوقتي. Am I right?
Yes.
احنا عدينا 10 دقايق.
It's okay.
طيب, okay, let us take this question from Nasser. Yes.
What is the minimum number of clusters?
What is the
minimum number of clusters?
This is a key parameter that you can set. يعني as I mentioned, إنه الباريتو set could reach to infinite size. You have hundreds of solutions. All are non-dominated solutions. What you need to get here is you need, مثلا, for example, you need only 20 solutions or 50 solutions or 30 solutions. This is a parameter that you can set. As you set the number of the population size, you can set also the maximum size of the Pareto set. So this is a key parameter that you can set here. Sometimes 20, sometimes 50. For example, in one of the paper that I published earlier, it was 50 solutions. And one of the reviewer mentioned that 50 is too much, so too many. So can you do it to 20 solutions? That's okay, 20 solutions, 50 solutions, 30 solutions. This is the parameter that you can set. So, okay, Nasser?
Yes, okay, Doctor. So it is based on the problem itself, the distribution of the solution itself.
Yes. Usually, if you have a real valued problem, لو optimized parameters are real, you will end up with very high number of the Pareto front solutions. So you can reduce them. Maybe in other problems like discrete problems or scheduling problems, maybe 20 is very high, by the way. يعني لأنه البروبلم is أو nature of the problem and the parameters are discrete, either 1, 2, 3, 4, and so on. So you have limited options. You have limited number of the Pareto size. But this is definitely problem dependent. Okay, so you compute the reduced denominator set bionitic with it. Okay, خلاص يعني you take the centroid and you get the nearest to the centroid and you eliminate the others and you end up with the maximum size that you need. This is just a GIF that I found in the internet, which gives you an idea about the clustering technique. So you measure the distances and you combine them. You measure the distance, you combine here. And if you need to reduce clusters more, and if you need to reduce clusters more, this is the nearest. You have here one cluster and you combine them. And this is another cluster. And this is another cluster. And the distance here is minimum. So you end up with one cluster then. But there is a major difference between this clustering technique that you show here and what we are discussing. What is the difference? If you look at this and what is the difference between this and the one we are discussed now?
Non-dominated.
اللي انت كنت بتسأل فيها يا ناصر قبل كده. اللي انت كنت بتسأل فيها قبل كده انه we take the average. Now here in our case we are not taking the average. This one is taking the average. Look at this and end up with this solution. We are not taking the average in our case. لأن the average could be unfeasible solution. Is it clear? Is it clear or not?
Yes, doctor, but why, if you allow me to ask, why it is acceptable here?
No, this is just to illustrate the concept of clustering.
Okay.
This is not. Let me say this is different from the clustering discussed earlier. And I would like here, but just this is introduced here to illustrate the concept of clustering. انك انت you measure the distance and then with the minimum distance you combine them as a cluster. But the major difference, as you mentioned, we are not taking we eliminate one solution and keep the nearest to the centroid. Okay, but is definitely this is different in that sense. Am I clear in this? Am I clear? Or you still have some doubts? I think by this we finished the clustering. So let us stop here and discuss the best compromise solution. How to extract. You have now 20 solutions of Pareto optimal set. If I ask you what is the best compromise solution with respect to all objectives, how to extract it, this is what we will discuss next class, inshallah. If you have any question, please ask. Otherwise, we can stop here.